All right, so yesterday we talked more about the Diels-Alder reaction. Specifically, we were looking at stereochemistry. We said that if you have two groups on the same side of your dienophile, that they're going to be on the same side as your final product. Most of that's fairly intuitive. What we're going to talk about today is something called endo versus exo addition in the Diels-Alder reaction. So what we're going to do is we're going to take an example reaction. And we're going to assess what the product might look like for this example reaction. And I'm going to use cyclopentadiene since we're pretty familiar with it at this point. And we're going to react this with a dienophile. All right, and just like before, we can have these carbons kind of dock with one another. And then this pi bond will hop over, will form a sigma bond. Pi bond will swing over, form a new pi bond. Then this pi bond will hop over to form a new sigma bond. All right, and then in this reaction, we're going to be making a new six-membered ring, and we're going to have kind of a roof going on here. And if you remember yesterday, I said you can even color code these. So let's zoom in on this. We've got that green carbon on cyclopentadiene. That's going to form this roof. So it's going to kind of flip up. And then over on the other side, we're going to form a new five-membered ring. It looks like this. And then we also have hydrogens coming off. So I'm just going to show those hydrogens as wedges because we can't have those hydrogens be dashes. The dash position is already occupied by our dienophile. So we formed two new sigma bonds. We formed a sigma bond right there. We formed a sigma bond right there. And then in addition to that, we formed some interesting stereocenters as well. So then the question is, how can we predict the stereochemistry for this system? And I think it makes a lot more sense if we consider the side-on view. So bear with me. I'm not the best artist. And we're going to do the side-on view of the transition state for this overall Diels-Alder reaction. So what we're going to do is we're going to show cyclopentadiene kind of docking on the top like this. And then we're going to show the other molecule underneath, that's our dienophile. And I'm omitting all of the pi bonds that are participating in this reaction. However, we do know that in this reaction, we're forming a new sigma bond between these two carbons, and then these two carbons right there, there, and there. Does that make sense? So it's kind of landing on top of it, so to speak. All right, we're also breaking this pi bond right here, so I'm going to show that as a dash. We're forming a pi bond right there, so I'll show that as a dash. Forming or breaking that pi bond right there, and then breaking that pi bond right there. So really, we've got this movement of electrons in this kind of ring system orientation. So we can go ahead and we can look at this. We can say this is one possible transition state. We know it's got to be kind of this edge-on overlap of p orbitals docking with one another. All right, so that's one option. And the other option is kind of something similar, but with a subtle difference. So in this one, we still have cyclopentadiene on top, but this time underneath, we're going to show the other molecule kind of tucked in. See how that oxygen's pointed underneath cyclopentadiene rather than sticking out and away? But just like before, we need to form a new sigma bond between these two carbons, and then these two carbons as well. Oops, sorry. Selected the wrong carbon. We'll keep it consistent and have it go to that carbon back there. And then we're breaking this pi bond. We're forming a pi bond right there. We're breaking that pi bond, and then we're breaking that pi bond. So it looks similar, but like I said, in one of these, it's essentially completely stacking on top of one another. The other one's more of an edge-on where it's pointed out and away. Does that make sense? So two possible transition states. This will impact the stereochemistry of our desired product. The weird thing that happens is that if your electronegative groups are tucked underneath, it actually stabilizes the entire system. And what I mean by that is this whole group being underneath is really, really stabilizing for the system. Another way of thinking about this is your dienophile prefers to be, let me slide all of this down. Underneath your diene in the transition state. You get this stabilizing effect of the electron withdrawing group actually stabilizing the formation and breaking of all of those various pi bonds. That means that this transition state is not usually preferred on the left-hand side. All right, does that make sense? So let's consider the final products. So for this one over here, we're going to go ahead and draw the side-on view. I really like seeing the side-on view. I feel like it gives you a clearer picture of what's going on here. And we're going to get kind of that roof effect of that cyclopentadiene. So like I said up here, that green carbon with the dot is going to be kind of tucked above and form a little roof. We're forming a new pi bond over here. And in this one, we said in the transition state that that oxygen really prefers to be closer to the pi bond over on this side, right? So what's going to happen is it would rather be kind of in this orientation where it's tucked closer, and then the hydrogens are further away. All right, let's compare that to the product for the other reaction. So I'm going to slide all of this down. All right, in the other reaction, we're going to get something similar looking, meaning it's still going to have that roof. Is it okay if I slide up? I know some people in the back have a hard time seeing. But this time, things are going to be down here, and the hydrogens are almost going to be like little legs sticking down underneath. So these are the two potential products we could get. The one on the top is called our endo product. The one on the bottom, which we said usually isn't preferred, is called our exo product. An easy way to remember this is exo simply means that something's pointed out further away from the system, right? So if you think about the thing that is now attached, meaning this entire group, it's kind of pointed out away from the ring system, therefore it's referred to as exo. Endo, on the other hand, simply means that the dienophile that was attached prefers to be closer to the longest bridgehead. So we can look at it this way and we can say, that's a 2-carbon bridgehead right here, right? So that group prefers to be closer to that bridgehead than that 1-carbon bridge up on the very tip top acting as the roof. can't spell bridge. There we go. At least I hope. All right. So usually in Diels Alder reactions, your endo product is favored. But just because chemistry is challenging, chemists have figured out ways to prefer the exo product. Usually that's done with some sort of special catalyst system to favor formation of the exo product over the endo. However, under most circumstances, without a catalyst, you favor the endo product. Yep. Where am I missing a pi bond? If we go up here, we only had one pi bond in our final product. But besides the CO double bonds, right?
Oh, right.
Yeah. Yep. So it is kind of abstract to think about, but the main takeaway from this is when your diene reacts, it really prefers to stack almost like pancakes landing on top of one another rather than an edge-on stacking of pancakes. That's a lot more stabilizing for this reaction. So that's kind of an analogy I use to think about it.
I have a question.
Yep.
So by saying favored, you mean it exists at a higher concentration?
Yeah, so then the question is, how do we define favored?
Yeah.
Does that mean exclusively one product over the other, or a ratio, meaning major and minor? It depends.
Okay.
Sometimes it's a major minor situation, sometimes it's exclusive. It depends on what diene and dienophile you're using. Yeah, that's a great question though. So then the question is, well, why is the stacking of pancakes favored over the edge-on stacking of pancakes? And what you have to do is you have to think about the orbitals for these. So you don't need to copy this down. But here's kind of an orbital view that I think helps explain this exact same problem we were looking at. So you can see on top, that's the endo version where the oxygen's tucked underneath and it's the stacking of pancakes, where the one on the right is the exo product. So it's kind of the side-on stacking of pancakes. And when you have the complete overlapping of pancakes on the left, you see how all of these orbitals are essentially lined up with one another. That's a huge stabilizing interaction between all of those p orbitals. That really lowers the activation energy for this reaction. Whereas over here, these p orbitals kind of hanging out over here aren't doing anything. They're just hanging out by themselves, not providing any sort of additional stabilization energy. Therefore, it has a much higher activation energy if it proceeds through that pathway. So you do need to think about it in terms of the p orbitals on your electron withdrawing group stabilizing the p orbitals on your diene. Yep. That's a good question. A lot of really smart people sat down and they looked at a huge amount of data from these reactions and they said, usually when I run this reaction, I get this product. I don't get the other product. Why? And then they came up with a bunch of different theories, and really the best theory that couldn't be refuted with other data is this theory down here, explaining it through orbital interactions. So it's one of those things where the theory that's used is there to support the data, not the other way around. We don't first come up with a theory and then have an experiment to validate that theory, right? It's typically the other way around. Although it is in many ways the chicken and the egg argument, right? It's a self-feedback loop where you're constantly trying to come up with reasons why your theory is supported and not refuted. Yep. Good questions. All right. So as far as we're concerned, in sophomore level organic chemistry, the endo product is favored, exo product's not favored. If you go on and take advanced organic chemistry, it gets harder. And there's going to be a lot of weird rules that you might need to remember. But for the time being, just remember endo product is favored. Make sense? All right. So what I want to do next is really quickly go back and talk about electrocyclic reactions that we talked about previously. And this is really, really, really quickly going to be a crash course. Because quite honestly, we don't have enough time. We got to get through the end of these last few chapters. But I did want to introduce them to you because I think they're fascinating. So in an electrocyclic reaction, you have a conjugated system. So typically you've got something like a trine or a diene, something like that. And like we saw before, these two ends can actually react with one another. So this pi bond can jump down and form a sigma bond. This pi bond can jump over and form a pi bond. This pi bond can jump over and form a new pi bond. And you can actually make a new ring system through this chemistry as well. So do you remember that from a couple days ago? The weird thing with this is it depends on how you're activating the reaction. Are you activating the reaction with heat energy, or are you activating this reaction with light energy? So let's go and look at this through another system. So down here we've got a conjugated diene. So in this system, these two ends are basically going to react with one another, right? This pi bond's going to jump over, form a new sigma bond. This pi bond's going to jump over, form a new pi bond, and you'll actually make cyclobutene. This is somewhat unstable though, right? It's a four-membered ring with sp2 hybridized carbons. They're not super happy being 90 degrees. All right, so the weird thing with this is in this reaction, we are using heat energy as indicated by this delta symbol. And so if we look at the HOMO level for this system, it's highlighted right here. In order for that sigma bond to be formed, you have to have constructive overlap of two in-phase lobes of a p orbital, right? And so you can see that over here, that this red phase that I'm highlighting and this red phase need to overlap in order for that sigma bond to form, which means that these have to rotate in the same direction as one another in order for those orbital overlaps to occur. This is called con-rotatory. So under heat conditions, we have to do this in order to get those orbitals to overlap. So because of that, one methyl group is going to be sticking up. You can kind of see that over here. And the other one's going to be sticking down because they're rotating in that same direction, right? It's kind of a little bit weird to think about, but big thing is each side of your p orbital is a different phase. We have to make sure that they're overlapped correctly in order for a bond to be formed. Yep?
So if you do with light, then it just excites the electrons and then they'll be cis.
Well, let's take a look at with light. So what do you think happens to that HOMO level if we bombard it with the appropriate energy of light? Yeah, we'll excite one of those electrons up to a LUMO level. In which case, this LUMO, or former LUMO, I should say, becomes our new HOMO level, meaning it's going to be our more reactive orbital. And if you remember, we've added new nodes. So we actually have two new nodes here and here. So our orbital phases have changed in our new HOMO level once we excite that electron. All right. Now, if we think about it, we need to get two in-phase orbitals to overlap, which means instead of those two orbitals rotating together, meaning in the same direction, they're going to actually rotate opposite in order to allow for an overlap. So over here, you can see this orbital has to overlap with an in-phase orbital on the other side, so they're going to rotate together, and this is called disrotatory. So this is like the bane of a lot of students' existence is they're like, I hate organic chemistry. It depends on so many different things, including whether or not you're using heat or light. And this is a good example of that. Up here, our product has those methyl groups trans to one another, meaning opposite faces. But down here, we get a completely different product where they're actually cis to one another. So we can favor one over the other by applying the appropriate amount of light energy or the appropriate amount of heat energy in the absence of light. It's kind of crazy to think about. This stuff is really fascinating, in my opinion. Again, that gets back to Ian's question. How did they figure this stuff out? This theory, in my opinion, was pretty ingenious in order to describe the observed stereochemistry for these reactions under various conditions. So this, I thought, was kind of interesting to talk about. Like I said, under heat, you have something called con-rotatory. And then this is disrotatory. what gets interesting is in this system we had a diene. With the triene, you have to think then about the HOMO levels for a triene, which is going to be different than the HOMO level for a diene. So it is kind of complicated. If you want to go through and read this section in the book, it's an excellent read, though. Yep. Oh my God. This is like, maybe I have undiagnosed dyslexia. Rotatory and disrotatory. I think it happens when I speak and write. My brain just gives up on one or the other. Yeah?
So heat and light are both forms of energy.
Yep.
They're saying that just heat is the lower form of energy.
It's different. Heat won't necessarily excite electrons up to a higher energy level. It just applies the energy allowed to overcome some sort of activation energy. Whereas light will excite an electron to a higher energy orbital system, and then that orbital system is now the reactive orbital system. Yeah, it's kind of weird. And students will ask me too, they're like, why are we covering all of this HOMO-LUMO stuff? This is a good example of it applying to understanding a reaction's mechanism and the stereochemical outcome. Sorry, I'll come back to you. Yep.
Does one take precedence over another? Like, you have heat and light, is it prefer one? Or
Oh, that's a good question. So if you have heat and light, you typically don't want to do that because you'll potentially get a mixture. So normally, if you want to favor disrotatory conditions, you literally run this reaction in the dark. Or sorry, in a light system. Whereas conrotatory, you would run it in the dark. So having light around does change things a lot. So one of my friends in grad school, she did chemistry in a glove box. I don't know if anybody's seen a glove box. It's the thing with giant rubber gloves sticking out, and then the chemist has to go in and stick their hands in through those rubber gloves into an air-free environment and do chemistry. Not only was she doing air-free chemistry, which required her to work in a glove box, but all of her chemistry was also sensitive to light, which meant she had to work in the dark in a glove box. We used to always joke that it was like the Wizard of Oz because she was behind a little curtain. But some of this chemistry is really interesting and challenging to figure out and to control appropriately. Yeah?
So what's a quiz or test question talking about this sort of thing going to look like?
So in general, I will say, quite frankly, I'm not going to put this on a quiz or exam, but I do feel like it's my obligation as an organic chemistry instructor to at least show this to you. This is pretty advanced. In my opinion, this is something that would be covered in more detail in an advanced organic chemistry course. The Diels Alder reaction, absolutely, I want you to know forward and backwards. Yep. All right, so the last sections are just kind of fun. You're welcome to take notes if you want. You don't have to if you don't want to. This is just about color and vision, right? So if we look at the top molecules, meaning all of those ring systems, those are called acenes and have been studied pretty extensively. The one thing you might notice with acenes is over here, when we have 1, 2, and 3 membered systems, that they're basically colorless powders, right? They don't have any unique special colors, but as soon as we get to tetracene, things get a little bit red, meaning it goes more orange. So this is redshifted. Why? When we go to tetracene, why is it getting redshifted? What? Has nothing to do with movement.
The higher the wavelength that it goes.
Smaller jump.
It's a smaller jump between the HOMO and LUMO. Do you remember previously when we talked about HOMO-LUMO levels? I said when we extend conjugation in and add more alternating double-single bonds, it actually gets redshifted, meaning it appears to be more red. It will absorb light of a lower energy, right? So it gets redshifted. Then the crazy thing is once you add another ring, is it getting more redshifted? It gets blue shifted. So this is something that kind of blew my mind in grad school and I didn't know about. And then the question is, well, why is pentacene getting blue shifted if increasing conjugation causes this to get red shifted? And so my lab in grad school actually worked with a lot of derivatives like this. And what chemists have found is that pentacene is ridiculously unstable. instead, a better way of drawing pentacene kind of looks like this, where you have all 5 rings. And then in the center, you have 2 radicals. So the question is why? Well, essentially the theory is that having 2 separate conjugated systems is more stable than having one continuous conjugated system. Therefore, it's acting more like naphthalene on each end than one giant conjugated system. And the reason for that is the HOMO-LUMO gap gets so small that it starts behaving in wacky, wacky ways. Chemists like a challenge, so pentacene was incredibly challenging to make synthetically because it's super duper reactive as a radical. What they did was they basically added big bulky groups to prevent it from reacting with other things, basically adding so much garbage around it, it couldn't find another molecule to react with in space. They've actually gotten these up, I think, to 12 acenes all in a row. So they're using these a lot in photocells because they have such low HOMO-LUMO gaps that they can absorb even down to IR light, which is pretty dang fascinating. Because if you think about sun energy, a lot of that is infrared, meaning we want to absorb that energy and turn it into useful work. So a lot of this is used in photovoltaics now, especially photovoltaics that are organic. All right, and then down below, I like this one down here. So vitamin A, if we think about it, is kind of this yellowish color. And then we go to beta carotene, that's more orangish. And then the next one is astaxanthin, which is what gives salmon its pink color. And this is a good example of more alternating double single bonds leads to a molecule getting redder and redder and redder, right? So this gets increasingly redshifted. In fact, a lot of the dyes that we use commercially, like this one, green number 3, is specifically tuned to have the appropriate amount of conjugation to give it a specific color. So if you ever look on the back of food labels, oftentimes it'll say like yellow number 5 or green number 3. They basically were able to study the amount of conjugation required in order to give a certain color. And then down here, you can actually see lycopene. It's kind of similar to vitamin A and beta carotene, but just with a ton of conjugation, which actually gives it its red color. So plants have done a lot of this conjugation chemistry already. It's pretty interesting, I think. All right, the last one that I think is really fascinating is the chemistry of vision. So if we think about our eyes are tuned to basically detect certain frequencies of light, right? So we've got rods and cones and things like that, but the way we detect certain frequencies of light is on our rods and cones, we have conjugated molecules of very specific lengths, basically to correlate to the HOMO-LUMO gap energy required for that specific photon, right? And what happens is we can have light hit the cis bond, meaning the cis alkene, and that is very, very reactive. When it has the appropriate wavelength of light, it will actually isomerize to the transform, and then the protein says, hey, I don't feel anything anymore. I'm going to send a signal to the brain saying that you're seeing this specific frequency of light. So really this all gets tied back into vision. All right, the last fun thing is about the mantis shrimp. How many of you have heard about the mantis shrimp? I showed people this already in the review session, but I think it's worth seeing again. So how many of you have read The Oatmeal? It's hysterical. I really recommend taking a look at his comics. But he talks about the mantis shrimp and why it's his favorite animal. And he talks about how we have these rods and cones in our eyes. Dogs have photoreceptors for green and blue. We've been able to study that. So dogs are colorblind. I know my dog, for example, I have an orange chucket, and I can throw it in the middle of a green field, and sometimes she looks out there and she's like, I have no idea where it went. It's because they don't have that orange photoreceptor, right? Which is ironic that they make chuckets orange. But I guess a green ball in a green field might be even harder. Either way, humans have 3 color receptors, which means we can then see colors like orange and purple due to the combo. Butterflies are pretty cool. They have 3 plus 2 additional ones. The 2 additional ones are thought to be IR, So when they're searching for specific flowers, they can actually look for those wavelengths and then seek out flowers of a certain type. And then the mantis shrimp has not 2, not 3, not 5 like a butterfly, but 16 different color receptors. So as far as we know, it's the world record holder for different types of photoreceptors. And then it goes on talking about a thermonuclear bomb of light and beauty. And then the cool thing is, if you look at these, they're super colorful, but they're also crazy violent. So you can't actually get these in a fish tank. You can, but you have to get a special fish tank because they can bust their way through glass. So basically the way that they kill their prey is by basically, I don't know if punching is the right word, but they can shock them with a huge force of energy and then eat them after that. And so what they're finding more and more is that the photoreceptors for these shrimp isn't necessarily due to the color that they need to see, but if you think about living in an ocean environment, you don't get a lot of light. But if you need to hunt, you need to make sure that you see prey, right? Because prey can hide in a low light environment pretty well. So what they think is that these photoreceptors, I like this, these photoreceptors are more about detecting movement in addition to light. So they can see really subtle movement. So even if prey isn't moving very much, they can pick it up like that in a low light environment. So this talks about the aquarium glass. Yeah. Yeah. I love this guy's stuff. He's fantastic. Anyways, I thought that was pretty interesting. The other interesting thing too, if you ever listen to Radiolab has a whole thing where they talk about color. There's a certain percentage of females that actually have an additional photoreceptor for a different type of red. The problem is a lot of people don't even know that they have it because they think everybody sees those colors, right? If that's what you were born with, you don't know that people don't see what you see. So they're actually going out and gene testing people to see if they have that mutation that gives them that extra photoreceptor. And if you do, I guess you can call yourself an X-man or woman. Yeah. Anyways. So the last thing is I did post a handful of practice problems at the end of this OneNote chapter. So if you want, I'll let you use these last few minutes to look at a handful of these problems. So I'll leave this one up for a minute, but see if you can predict the 2 starting materials that would be required to make this product, then provide the mechanism. And then I've got a few other book problems if we have time.